Thank you, Megan. Good afternoon, everyone. My name is Austin Roy. I'm a reporter for Group 4, and I'll be discussing our results from the experiment we did last week. So, first thing I'll talk about is what I'm going to be talking about, and that is, first thing I'm going to do is just a brief introduction on the actual time constant itself, because we didn't have a chance to discuss it with the leaders, because we didn't have it last week. And then we'll do a quick reflection on the actual experiment itself and how that went. And then most of this presentation will be done on the actual analysis of the data we collected. And then we'll do a comparison between one of the other group's experiments, and then we'll make some conclusions based off of that. So the first thing we'll talk about is the actual thermal time constant itself. I think we learned a good bit about this in system dynamics, but just as a refresher for it, basically the idea of the thermal time constant is it's a measure of time. That actual time is a percentage of your difference between your initial and final data, and that percentage is calculated using the general exponential function. So basically the one time constant is 63.2% of that data difference. It's a good way to summarize exponential data plots. And your larger time constant, in our case for our experiment, that's going to be a slower thermal response versus a smaller time constant, which is going to be a faster thermal response. So next thing, of course, is the actual experiment itself. Our group, we did the ice water, some safety considerations, especially for the boiling water experiment, wear glasses, clothing, gloves, and just being overall careful handling. As far as the actual experiment goes, when we used the thermocouple, we made sure it stabilized at ambient temperature. We inserted the probe and then made sure it stabilized there, pulled it out, wiped it off real quick to make sure that the thermal conductivity of the water on it didn't affect our results. And then what we did notice is the actual ice water, especially from my data, it got down to about 8 degrees, which we expected to be at 0 degrees, but because we only poured the water in just before, like when we just got into the lab, it didn't have time to get cool enough. And then our data sampling rate was 200 milliseconds. This was pretty good. The only issue we saw is we didn't have a whole lot of points for that initial temperature change. Just briefly going over the lump capacitance method that we used during this experiment. Really what we need to get out of this is just that it's an assumption we're making. And that assumption is that the thermal gradient of our temperature probe is consistent throughout, and that there is no resistance to, we're neglecting resistance to conductivity. So basically we can say, okay, the thermal conductivity of this probe is infinite, and we can make some easier calculations. So this is the raw data for our portion of the experiment. You can see it starts at about 22.5 degrees Celsius, which is our ambient temperature. You can see we insert the probe, it goes down to about 8 degrees, and like I said, it doesn't get any cooler. The water is actually cooling while we're doing this experiment. And then when we pull it out, you can see it start to rise towards ambient temperature. We stopped it before it got there. This is just a separation of that same data, so you can see the difference. We don't need to spend much time on this. This is the plots for the normalized data. Essentially for the normalized data, we just basically scaled it down so that we can work with it better. Our temperature, T, is just the temperature we collected. Our temperature infinity is the temperature of medium, which is water, which we put at 0 degrees, but it was actually around 8. And then our initial temperature, that's at T equals 0 for each of these. So the actual time constant was calculated from that normalized data, just taking that natural log of that, and then using that plot, we set a curve fit to a linear curve fit, and the inverse of the slope of that curve fit is our time constant. So this is for the water, this is for the insertion of the water into the water, ice water, and the tau of our curve was 1.09, and the tau experimental, which is like a manual calculation, was 0.6. So there is a little disparity between those, but overall not too bad. Steady state approximation was 5 tau, which is 3 to 5 seconds, and it looked pretty consistent with our data. This is for the removal, so same process, but thing to note is our tau is much larger, and that's because the thermal response is much slower whenever you take it out and let it equalize with air. This is for the other experiment, boiling water, so everything's going to be the same here, except of course our time constants are going to be different. It's all the calculations we don't need to go over again. They started at an ambient temperature around 22 degrees as well. Worth noting, their data did come out a little better than ours. You can see for boiling water, it's easy to tell when boiling water is at its equilibrium temperature because it's boiling. As for ice water, it's kind of hard to tell because it doesn't do anything specific that you can like just look at and tell. When we did remove for this experiment as well, we stopped at about 30 degrees, but we know ambient temperature was lower than that. So we're going to see some disparity results from that. This is normalized data, once again, just scaling it. And then as far as time constant goes, this was pretty good. The actual curve fit and the experimental data were very close to each other at 0.4 seconds. And this is the removal, once again, larger, slower thermal response once you take it out. This is a comparison with the group that did the experiment, the class after us. And what we saw was a big standard deviation between our results. And I do think it's a big difference because their data was stopped at different points than ours. And like I said, our ice water wasn't cool enough. But what we can conclude just from looking at the difference between when it's actually in the water and out of the water is that our thermal conductivity of water is much greater than air. Just to kind of conclude, learn a lot more about time constants than I knew before. It's a very useful tool for describing a transient response like we just did. Thermocouple, it reacts much more quickly to temperature changes in water as opposed to air. The experiment can vary widely depending on your data or just whether or not you're doing it consistently.